Okay, so let's look at another question. Oops, sorry about that. So let's look at another question and see how another reaction that you ought to know for your next exam. So let's say you had this situation where there is a oxygen on top here, and then there's a nitrogen there. Then also here you have a nitrogen. Then basically we want to produce, ultimately we want to produce a bunch of reactions. Basically we want to produce a situation where you have this situation plus a CO2, right? So please take note that the only thing that's been removed is this carbonyl group. So let's see how that works out. The conditions here are sodium hydroxide. We're really interested in the base, okay, and also a halogen, which has been bromine, like that. So let's see how that works out. So I'm just going to rub all this, and then we can get started. So the first thing that we're going to do is deprotonate our parent structure, meaning we're going to remove a hydrogen using the base. Remember, we have a base, so we're going to use that to deprotonate the structure. So forwards and backwards, we're going to use the base here to deprotonate our molecule, right? So that hydrogen has been removed, and then the following, what's going to result is a deprotonated version of this particular molecule. So we have then the nitrogen now with the minus sign because it has less than it likes, less bonds than it usually likes to have. So we have a minus sign there. And then we've got the hydrogen still sticking out at the bottom there. Then we have an introduction of our halogen, which is the bromine group, right? Which is the bromine group. So the halogen basically will be abstracted by the nitrogen, causing the electrons to fall onto the other bromine like that. Okay, so that we can say, as a result, we are going to have this situation where we have an oxygen there on top. Then now attached, we've got a bromine attached here on the side like that. Okay, then just like we did at the first here, we are going to deprotonate the molecule with a base. This is a very strong base, hydroxide. Okay, so it's a strong base called hydroxide, which we're going to use to deprotonate this particular molecule. Okay, and when we deprotonate this molecule, what's going to happen is that electrons are going to fall back onto the nitrogen like that. Okay, sorry about that. Going to fall back onto the nitrogen like that, so that as a result, we are going to have, let's use a black pen. So as a result, we are going to have this situation where there's a nitrogen sticking out there at the bottom with the minus sign like that. Okay. There's a minus sign at the bottom like that because it has less bonds than it likes to have. So that's the reason why we've got that. So this is called a rearrangement reaction. It's called a Hofmann rearrangement reaction, and we will show you where the rearrangement takes place. So this next step, then since you have an excess of electrons here, and electrons are the ones which make the movement, the electrons will actually fall and make a double bond between the nitrogen and the carbon. When that takes place, this whole group will come and attach itself onto the nitrogen, causing the electrons to fall onto bromine like that. Okay. Then, with the removal of bromine, right, we're going to have this situation where you have the oxygen on top, and at the bottom you have that situation. I'll write the carbon here just for clarity, so we don't get lost. There's a nitrogen still there, and yeah, we still have a nitrogen there at that end, not so. And then you remember this bond here has moved from where it was attached to previously attached here, but it has then moved onto the nitrogen. So that's why we have that going on there. And then we have an introduction of an OH. Now this is a very peculiar or interesting use of an hydroxy group, because the hydroxy group usually serves to take hydrogens. But in this case, it's going to attach itself onto this molecule, very strange, very rare, causing the electrons to fall onto the nitrogen in that fashion. Then when you go ahead, go forward, you'll find, so we're going to start with this one which has been attached. So we have the OH, which has then been attached, going down. Then this carbonyl group, I'm just going to shift it going this side. So it's still there, it has not been affected. So we have the carbonyl there. Then the nitrogen was also still there, like that. And then we also have the other bond like that, the ethyl group there. Okay. Now, the next thing that's going to happen, since this nitrogen still has 2 bonds, is that it's going to cause the electrons to fall onto this bond here, causing the electrons again to do just that. Okay, and then so I would ordinarily write this in a okay, so basically what happens is that, so we're going to say forwards and backwards like that. So as a result, you're going to have an oxygen with that situation. Okay, so this oxygen here has got a minus sign like that. I'm just trying to make use of this space so that we won't have to go to a new page. So you have a double bond here now, right? And then there is, of course, this. I've just drawn this for the other end. Now this molecule is in resonance with this structure. So there's a difference between what I'm about to draw and the ones I've been drawing so far. So this structure means resonance. It means an the true molecule is actually, can we say that the average of both of these, right? So this structure here is actually in resonance with this molecule that I'm about to draw, where you have the oxygen on top here with the minus sign going on there. And then we have the nitrogen here with the hydrogen like that. Okay, and then you have this. So how this one basically came about is, instead of the electrons basically making a double bond, what they simply did is abstracting that hydrogen from there. That's what basically made this one here. So this one, which we have just drawn with the last one here, is allegedly in resonance with this molecule here. So you just have to settle with one. So we'll just start with producing this one and saying it's in resonance with that one. Okay, then at this point, we're then going to proceed. Let me get my pen. So at this point, we're then going to proceed. So we say what happens next is that this bond will form a double bond because the electrons are in excess there. Then between this carbon and the nitrogen, this bond will break, it will cleave, causing the electrons to fall onto the nitrogen, the way we've been doing here, and also here as well. But instead of it staying on the nitrogen, it will actually go out of its way to abstract or remove a hydrogen from a nitrogen, a hydrogen from an acid, right? So that's what we're going to have as a result, meaning that the nitrogen, having obtained the electrons, will abstract the hydrogen from there, causing electrons to fall onto the nitrogen like that. And then what you're going to have as a result, so I've said this bond has broken, so we're going to have here hydrogen with nitrogen with a hydrogen on top, still with that, and then we have another hydrogen added to it like that. And then between here and here, this is a carbon, this is also a nitrogen, so we're going to have carbon dioxide like that. Okay, and then we also have the molecule H2O like that. Okay, so that's how you go about this particular question. Let's say you had a situation where the molecule you're given is, say, this ring. This is, I think, the last one that we'll do. So you have this ring structure, okay, and then you have this going on as well. So when you show those dark, this indicates that this CH3 is behind. That's all that means, okay? So this one is called a pinnacle rearrangement reaction. So let's see how this one works. So the first thing we're going to do is protonate the hydrogen that's on top. So we're going to protonate the hydrogen that's on top, like that. So we have a hydrogen here, protonated. Okay. Of course, the nitrogen at the bottom there as well. I like to circle my charges. I don't know, it just looks fitting. So we have a forward reaction, meaning that our molecule here now, this hydrogen, this OH at the back, now has an extra hydrogen. And so it will be positively charged. Because oxygen likes to have 2 bonds, now it has got 3. So we have this situation where you have the CH3 on this end. There's also CH3 on top here, so don't forget that. Then you have this scenario here, OH. Okay. So the next thing that's going to happen is that all by itself, because of the formation of a stable carbocation, you're going to have this molecule leaving the structure because the resulting molecule is going to be stable. All right. Maybe on another video we can talk about carbocations and stability and so on and so forth. But for this video, we just want to solve the question here. Okay. There we go. So the next thing that's going to happen is that the electrons will fall onto the bottom here, and then the one that's going to move. Okay, so we're going to have a rearrangement. This is where the rearrangement is going to take place. It's the one that's going to be, it's the one which is equally behind or at the back. So we're going to take this one, and that's the one which is going to move there. Okay, so that as a result, we are going to have this one at the back. Okay. Then we go down, we go up. Here there's a double bond connected with hydrogen like that. in that fashion. Okay. And the final thing that we're going to do is abstract the hydrogen from the bottom there using a weak base, which is water, right? So we're going to use water to abstract the hydrogen at the bottom there. So the hydrogen will be abstracted there, causing electrons to fall onto the oxygen, giving us our final structure for this one. Okay, so we have this as our final structure. So this, of course, will still be at the back. And it makes sense because the closest one to replace the departed OH2 should be the CH3, which is at the back already. So that's basically that for this particular equation. Now, what if, and this is the last one that we'll do, what if we protonated the other one? Let's see what happens. So we protonated this one. Let's see what happens if we protonate this one and see what we come up with then. So if we do that, we are going to have a protonated hydrogen. So it's the same procedure. Actually, this reaction happens both ways. You're expected to know in most cases, both scenarios. So please make sure you know how to do both. But it's really the same thing repeated on the other one. Okay. Then you have the oxygen here. Yeah, so if you want to try it out, you can pause the video and see the answer when you're done. Okay, so if you've tried it, let's see what happens. So we're going to protonate this oxygen using an acid. So let's use a black pen just for consistency. So we have an acid there. So OH, then 2 like that. Okay, double bond, perfect. So, oh no, we have the positive charge here. So we need to always indicate, please make sure you indicate at all times the charge. Yeah, so that's basically what we have. Then we go forwards. This is mostly a forward reaction. No back reaction going on here. Okay, so we have this situation here. Okay, then OH there. Then you have going down. So now our molecule at the bottom here has been protonated. So it's got 3 bonds, meaning to have a positive charge, a formal charge of +1, meaning that it's got one extra bond than it usually likes to have. And that's the oxygen we're referring to. Okay. So we have, of course, the CH3 here, and then we have the CH3 there as well. So just like in the previous case, the electrons will, this oxygen with 2 hydrogens will leave by itself, and then what's going to result is a carbocation. So we still have the OH here sticking out here, having a good time. I don't know what it's doing. Maybe it's thinking about its life. And then you have the CH3 here at the side here. What's missing is the OH, so we're going to put a positive charge there. Okay. So that's going to be the case, right? So the next thing that's going to happen is that the electrons are going to fall down here, causing this bond, so between here and this carbon and this carbon is going to break, making an attachment to take place where that H2O has just left. So even here we can say minus H2O to show that we've removed an H2O there. So we go down at the bottom. So now we're going to have a 5-membered ring. So let's see, this is the ring expanded. So if we start counting from here, we have 1, then 2, then 3, then 4. Then between this carbon and that carbon, where the attachment is going to be, right? We're going to have 5. So we can go ahead and proceed to draw a 5-membered ring. So you have a 5-membered ring like that. Then on position 1, so now this only works for single bonds. When it becomes a double bond, we just go straight and do that. Okay, so please take note. We don't have this situation with a double bond. We don't have that. Okay, so we have one still sticking out like that. Okay, and then you also have the CH3 like that. Please make sure you circle your charges in that fashion. Okay, and then the final thing we're going to do is simply abstract the hydrogen from there using a conjugate base. Use a black pen. Okay, so we're going to have that. Then giving us our final structure, which is this right here. So you have this molecule here, oxygen, and then you have the CH3 there at the bottom. Then you also have another CH3 here on the side. So that's how you solve this kind of question. I hope this video was helpful. If you have other suggestions of videos you want me to make, please comment below. And yeah, I guess we can look into that for another video. So thank you so much. Have a nice day.